favorite.
Nice steady word. And this is for the answer for the first one. And so, if the first one is diastereomers, you know, this is diastereomers, this is inaccurate. If the second one is diastereomers, well, you know, this is diastereomers, this is for. If you write more than one answer, even if the first answer is right, I'm going to mark it wrong. So don't take it personal. I want one answer. I want it to be clear where your answer is, not me guessing what your answer is. Please.
One.
All right. So now we're moving on. My plan was to skip the first 80 slides. But then I thought, I'll run through the first 3 slides. I'll tell you why. Because the first 3 slides talk about enthalpy of reaction. Remember enthalpy from second one? Entropy. Come on, say yes. Spontaneous reaction. Remember that? Yeah. So these things are not, I mean, yes. Yes, enthalpy, just like we learned in Gen 1, some reactions are exothermic, some reactions are, and that includes organic molecules. Entropy, some molecules become more organized, right, or less freedom, and some molecules gain more freedom, which is entropy, and that applies to organic molecules. Same thing, some reactions are spontaneous, some reactions are. That also applies to organic chemistry. So I'm going to skip through these, not because I don't think they're important, it's because I know I want to get to the important stuff. So enthalpy is the measure of heat, the amount of heat generated or consumed during reaction. Some reactions are exothermic, they release heat. Some reactions are endothermic, they consume heat. And by the way, organic chemical reactions are no exception. Some organic chemical reactions are exothermic, and some organic chemical reactions are endothermic. It's just the way it is, just like all the other reactions you have learned about. And the way we measure a reaction, whether it's exothermic or endothermic, which means whether so exothermic means the reactant have more energy than the products. Endothermic is the opposite. The way we measure it is we measure all the bonds broken and formed, and we add them up. If delta H is negative, reaction is exothermic, right? When delta H is negative. When delta H is positive, reaction is endothermic, right? And that means the products have higher energy. So just to let you know, like for endothermic, you gotta go up the hill. You gotta go from lower energy to higher energy, whereas for exothermic, it's the opposite. The products have less energy than the reactants, so they're more stable. When they say more stable, think about energy as water, right? Water always wants to go to the top. If we pour water on the top of the stairs, it will come down. If we pour water here, it's not going to come up the stairs. Right? That's common sense. And the same thing for energy diagrams. So a reaction that has higher energy for reactants than the product is said to be exothermic. Reactions that have higher energy for the products is said to be endothermic. So when delta H is negative, reaction is exothermic, and when it's positive, reaction is endothermic. And so organic molecules, without any exception, organic reactions, and this is an example of organic reaction, can be exothermic or endothermic. Entropy measures the freedom that the molecule gains or loses. I want to just tell you about one, because this is for organic chemistry, which I know I taught most of you in Gen 1. And entropy increases from solid to liquid, and from liquid to gas, because the freedom increases. So I'll give you an example. In a solid phase, let's say water. The only thing a molecule can do is vibrate and switch. That's all it can do. It can't do anything else because it's stuck in the same position. So what it does, it stands there and it's forever vibrating. It's constantly vibrating. Once that solid melts, say water, and now water is in the liquid phase, water can still vibrate, but it also can move around slowly. Like when you know water, the water molecules are constantly, but slowly, moving from one place to another. So it gains more freedom. When you go from liquid to gas, the molecule can vibrate, it can jump around from one place to another, it can go wherever it wants, it gains more freedom. Now, that's fine, and I taught most of this in Gen Chem, but for organic molecules, there's even more freedom that you don't think about. For example, hexane, liquid hexane at room temperature, has freedom. What does hexane do? It can do this, right? If you take hexane and just after hexane, make it into hexane, it gains a lot of freedom. Why is that? Because now this can rotate, and this can rotate, and this can rotate, and this can. Whereas when it was in this position, it didn't have that choice. It can only go back and forth between share and share, right? Whereas when we open it, it can rotate in many. So a cyclomolecule has less freedom than a linear molecule. So that's something I didn't teach you in Gen Chem, but just keep that in mind. So molecules in organic chemistry follow the same thing. The more freedom a molecule has, the higher its entropy. And of course, entropy, when you have a molecule stuck in one place, if you open the container, you get more choices. Like, I mean, if I lock you in here, then you can leave, your entropy is less. If I open the doors, and you freely do whatever you want, that means you have more freedom. It doesn't mean you're going to leave, but I mean, you will leave in about 20 minutes. But you have the choice. Like, nobody's forced to be here. You have the choice of leaving, and the entropy will. So the entropy of the universe is always positive. Just keep in mind, in organic chemistry, this is unique for organic molecules, unlike Gen Chem. When you open a molecule, it goes from cyclic to acyclic, it will have more entropy. And of course, finally, what really matters is entropy and enthalpy combined together will tell us whether the reaction is spontaneous or not. And also, for reaction to be spontaneous, delta G must be negative. And so, for delta G that is negative, the reaction, what does that mean, the reaction is spontaneous? It means the reaction will just happen by itself naturally. Where reaction is not spontaneous, it doesn't happen by itself. When I say it doesn't happen by itself, it doesn't mean that it will not happen. It actually can happen, but we have to do work, right? Like for example, if I let go of my keys, okay, they will spontaneously fall, right? That's a spontaneous reaction. The keys, no matter how long I spend here, the keys will not spontaneously go back to my. As long as if the keys jump from the table to my hand, we'll all be impressed with the magic, right? I mean,
But I'll be
I
dead.
stand here for forever and the key. But can I get it? Of course, I can do work, right? When I did it, I actually did work. Now, everybody knows professors rarely do the actual work, right? That's a fact. All right, so now think about this reaction. This reaction actually proceeds because delta G is negative, but did the entropy increase or decrease? It decreased because we went from two molecules to one and less freedom, but the enthalpy is. So when delta G is negative, the reaction is said to be favored and it's exergonic, you want to remember that. And when it's the opposite, it's endergonic. These are the same kind of nomenclature they use for exothermic and endothermic. Now, what does it mean when the reaction is that equilibrium? that means delta G is 0, right? And so delta G is 0, there it is, reaction equilibrium. That means the reactants and products are still going back and forth, but the total net is not changing. So if you have 10 moles of products and 20 moles of reactants, even though the reactants go to products to reactants, at any time you stop the reaction and you measure, it's going to be 10 and that's what equilibrium is. And we measure the equilibrium by constant, which is products divided by reactants raised to their stoichiometric coefficient, which most of you learned in Gen Chem 2, not really that significant for us. As a matter of fact, most organic reactions are not equilibrium reactions. As I said, I wanted to skip them, but I won't. What does kinetic tell you? Kinetics, all it tells me how fast or how. Just because the reaction is fast or slow has nothing to do with, no relation to delta G. If reaction is fast, doesn't mean it is spontaneous. Just means once the reaction happens, it will move really fast. If reaction is slow, it doesn't mean it's not spontaneous. It just means this reaction is slow. Some reactions, we want them to be fast. Some reactions, we want them to be slow. So just to let you know, because we always like things to be fast. In chemical reactions, especially in biological reactions, it all depends. I'm going to give you 2 examples from our bodies. If you have a headache and you take a drug, some kind of over-the-counter medicine, you want that reaction to work. Because if you have a headache, you don't want to wait 3 days for that drug to work, right? If I have a headache now, and I take 2 pills, I'd like my headache to go away in the next half an hour, right? I don't want to wait till Wednesday. I don't wait till Friday, right? Because that would be silly. In that case, if I'm going to wait 3 days, I might as well not take the drugs because that's. But also, there are some chemical reactions we want them to be slow, right? Like the chemical reaction of aging. Does anyone here want to age pretty fast? Oh yeah, I wish I could get really old really fast. People spend lots of money on striving to stay young, right? Why is that? Because we want to slow. So not all chemical reactions that are fast are good, and not all chemical reactions that are slow are good. Some chemical reactions, we want them to be appropriately slow. By the way, the slowest chemical reaction we'd like to have, slow, is the chemical reaction that sustains life. Because our life is a series of chemical reactions. Once they run out, we die. Nobody's in a rush. Nobody's like, can you create a medicine that will really speed up that process? Yes, it's called the gun. Freaking medicine. So nobody wants to speed up that reaction. Right? We all want to have that reaction slow. And so kinetics just tells us whether the reaction is fast or slow. And of course, how do you make the reaction fast? Increase the concentration. The most obvious one is temperature. Catalyst increases the reaction, activation energy. And I want to circle this because this is new. This is not in Gen Chem. So geometry and sterics, and we're going to learn about this in chapters 7 and 8. The shape of the molecule determines whether the reaction can proceed or not. So our organic molecules, because they could be linear, right? They could be linear. They could have many branches. Right? They could have many branches. That determines whether the reaction is fast or slow. You're going to learn later on in the next chapter that for certain reactions, linear molecules are a lot better than branch molecules. And so they proceed at a much faster rate. And that's something we're going to learn in the next chapter. So the rate determines how fast the reaction. Again, this is review. Reactions could be first order. What does first order mean? First order means the reaction depends only on
that thing.
one molecule.
Yeah.
depends only on one molecule. That molecule by itself can determine the reaction. As long as you have that molecule, the reaction can proceed. Right? So I'll give you an example. Studying, right? If you want to study on the weekend, that only depends really on you, right? You can decide, I want to study or not. Nobody can force you to study. Your mom can't force you to study. Your boyfriend slash girlfriend can't force you to study. Right? You can decide to study or not. That's a first order. A second order reaction is a reaction that requires presence of two molecules, right? Studying is a first order reaction. Smoking weed is a first order reaction. This is done in mom's face, but it's smoking. Now, being in a relationship is a second order. You need two molecules. Unless you're smoking weed and imagine you didn't see it. But that's a second. So the second order means we need to be present in order for the reaction to proceed. First order reaction depends only on one molecule. You don't need anything else. As long as that molecule is present, that reaction will proceed. Second order, if you have only one and not two, reaction can proceed. You must have more. And of course, I want to tell you, you're not going to see third order reactions in organic chemistry. But a reaction could be a third order one. That means we need three molecules to be present in order for the reaction to proceed. In organic chemistry, the reactions we're going to cover are going to be first order and second. As a matter of fact, chapter 7 is about first and second order. These are the factors that influence whether the reaction proceeds or not. Okay, I did say I was going to skip the first 30 slides. And it turns out, so I'll go back. So reaction could be thermodynamically or thermodynamically, and that means could be fast, but doesn't happen, or it could be favored that it will happen, but it will be slow, and it could be both. When you have a energy diagram, and this is an energy diagram, all the energy diagrams you've seen so far are something like this. That means reaction go to reactants A, whatever it is, go to product, right? Reactants go to product, and this is known as the transition state. Transition state. But just by looking at this diagram, what I can tell you is that reactants go to products in one single step. One single step. Right? It's just whatever the transition state is, it's one single step. In organic chemistry, some reactions go from reactants to products, but they don't go there in one single step. Some of them go in one single step. Some of them require more than one step. And because of that, we draw something that looks like this. So the greenhouse tells me that these reactions go from reactant to product here. Three steps. I want to tell you that you can actually look at the energy diagram. I'll come up with a couple. Okay. So if I have an energy diagram that looks like this, that tells me, and by the way, I drew that on purpose. Reactants are higher energy than products, so this reaction is exo. Okay, great. But the one I drew, drawn by 5-year-old, is two humps. That means that reaction happens in two steps. If I draw this, the action happens in one step. The action happens in four steps. So this reaction happens in 3 steps. And I want to tell you about them. When you read this. Each half of these is its own transition state. So if we have a single step reaction, it just has one transition. So this reaction has 3 transitions. Whatever is here are known as intermediates. Intermediates are usually positively charged or negatively charged ions that are extremely unstable. That means they'll stay there for a fraction of time, usually in the order of billionth of a second. That's how short, to get to the next step. Right? So keep in mind, so these are intermediates and these are transition state. But this reaction is a three-step. So if a reaction is only one single step, there are no intermediates, it just happens in one single step. Okay, so transition state is what happens between reactants and products, and in this case, just as before, we have methyl bromine and we have methyl chloride. So basically what happened is the chlorine replaced the bromine. So the transition step, the chlorine came close to the molecule and the bromine left. And it happened at the same time. Because if it happened in more than one step, I'll give you an example. If the bromine left at step one, and then the chlorine attacked that step two, that would be a two-step reaction. In this reaction, it all happened in one step. I'll give you an example of how that happens in our life. So if you want to buy sugar wine, you call that buy sugar wine. Doesn't mean you want to buy sugar wine. If you want to buy sugar wine, it happens in a two-step reaction. Number one, you go online, you find shit. You click on it, you pay. Right? You say pay, you pay. That means, so let's say whatever shit you want is $10. So you send them $10. That's step one. Step two, a day or two later, they send you a whatever shit you want. Right? So that's a two-step reaction. You send them your shit, they give you shit 2 days later. When you go to when I was in the Bronx and you want to buy weed, you go to the corner. I don't know, I haven't been, do they still sell weed at the corner in the Bronx? That's when weed is legal now. Makes it all like shitty. By the way, what you do is you take the $10, right, hold it in your hand, you go to the weed dealer, and what you do is, you say, what's up? What you do is, you don't send them the money because you don't trust the drug dealer. So you give them the $10 at the same time they give you weed. It's not two separate steps. It's not like there's $10 each, maybe stuff. But it happens at the same time. So here, the bromine is leaving and the chlorine is taking its place at the same time. That is one single step. Ordering online is actually something leaves, like $10 leaves your account, and 2 days later you get stuff. So keep in mind, the transition state of one means reactions happen in one single step. If it's two, right? Bromine left, there's the intermediate, and then the chlorine took its place, right? We send the money away. We send the money away, step one. 2 days later, we got a replacement for the bromine, which is the chlorine. That is two. It's the same reaction, by the way, I'm going to show you. This reaction, the chlorine replaced the bromine. This reaction, the chlorine replaced the bromine. In the first one, it happened in one single step. In the second one, it happened in two steps. And by the way, organic chemical reactions, we have to be able, if we figure out whether they happen in one step or two steps, we can tell what the product is and makes life a lot easier. And so, in this case, this is an energy diagram that shows that this reaction happened in two steps. You send your $10 away, and you get the, that's the bromine, and 2 days later you get shit, which is the, so the, Hammond Boston basically says the transition state determines how the product looks like, and you can look at the transition state. And you can see in this transition state that it's closer to bromine, so it looks more like this. And so if it was skewed more towards, I'm going to exaggerate, if it was skewed more towards the product, it would look more like the product. That's all I'm saying is that if it's in the middle, it looks like exactly in the center, but if it's closer to one side than the other, if it's closer to the reactants, it looks more like if it's closer to the products, it looks more like the products. And you can tell, right? In this case, it's closer to the reactants than the products. So in the middle, it should look more like the reactants than the products. And as you, of course, if I ask you how does it look like here, guess what? It would look more like the product, a lot more like the product. And that's what the anode postulate. And so I was planning to skip all these, but I didn't. I'm not that good. What I'm going to do tomorrow.
Yeah.
I will talk about this one thing before we go. So electropod and nucleopod are what drives all of the and you probably noticed on the last exam, I gave you a lot of questions on acids and it turns out what determines how strong a nucleopod or an electropod is the same trends we use for acids and bases. So the stronger the base, the stronger as a nucleopod. And that's why I wasn't really trying to torture you, but I was trying to get the point across. And so if you have, again, common sense, right? You have a negatively charged ion versus neutral, which one is more basic?
Negatively charged. Yeah.
Negatively charged or neutral, which one is more basic?
Negative.
Negative. Therefore, it's a better nucleophile. So nucleophilicity, which I'm going to talk about tomorrow, parallels basicity. So if you understand which one is more basic, that's a better nucleophile. And guess what? Electrophiles are the
Opposite.
opposite. So electrophiles are the ones that are more acidic or more positive.
Positive,
right?
yeah.
So if we have neutral versus positive, positive is more acidic, and positive is more
Negative.
So the idea that we spend time on about acids and bases is related to nucleophiles and 9528 1272.